Okay, this section we're looking at 1.3 with differential equations as mathematical models. I would read through the textbook pretty carefully and look at the models that they're talking about throughout the section. A lot of it you can pick up from the wording of a problem once you've got a particular problem type. So for example, if you're going and doing population growth, that if you end up having a quantity, which is, say, the population over time, if it's growing exponentially, that's going up like this, then how fast the population is growing is the derivative dp dt, and that's going to be proportional to or a constant times the size of the population. So that's one particular model for population growth. And if you're going through and doing radioactive decay, that's another example where it's coming down over time. And so you've got the population, or the quantity, I guess they use the letter A in the textbook, as a function of time. If you've got A as a function of time here on the axes, that's going to be proportional to a negative number. Because you've got exponential decay. Another example that you have that's in the textbook is Newton's law of cooling. And that comes from if you end up having the temperature, let's say you're either, that's the surrounding temperature, so it's T sub m or T sub s, depending on when it's surrounding or medium. And then you can have either the temperature coming down to it eventually, or if it's cooler, heating up to it eventually. Either way, depending on whether the value is, you're starting off the initial condition above or below, the derivative, the change in temperature, capital T, as a function of time, little t, is going to be proportional to the temperature difference, the difference between the temperature and the surrounding temperature. So either that's a T sub m or T sub s in the problem. Then we have things like where in the textbook they're talking about mixture problems, where what you have is you have a vat of mixture, and then you have some things being poured in, and then potentially some things being drained out. So the typically what you're looking at is a salt that's going into the water, and so that salt solution is mixing up and stuff, and so they'll use the letter A. So how fast that amount is changing is going to end up being the rate coming in minus the rate going out. So if it was pure water coming in and there's only a certain amount of salt in there initially, and then you're pouring water out, then the amount coming in would be 0 because you're not adding extra stuff in, and then what you're doing is the amount coming out is then going to be the quantity, A over the entire volume, that density coming out type thing. So there are some examples in there that we'll be going through and looking at over time. LCR circuits. So if you've got voltage, okay, so there's the voltage, and then you've got something called inductance, which they use with a little L thing, and then we've got resistance, which is sort of a squiggle like this, a broken line segment. And then we have capacitance, where they have a constant C. And so you're thinking of voltage as a function of time. And so voltage is going to be current times resistance. So if you have a current that's running around a circuit, You can think of it as like current running through water, and resistance being things like rocks in the way that's slowing down how fast it's running. So the resistance are things like light bulbs that are giving off heat, or light that come up and pick up some stuff. Then the voltage involving an inductor is an L di dt, so it's involving the derivative of current. And current is going to be the derivative of charge, which is represented by Q. And so the voltage for a capacitor is going to be 1 over C dq dt. So if you're ever doing something that's involving a capacitor and a resistor, you're going to get everything in terms of quantity. Sorry, that's QT. 1 over CQ. So you go through and fix that. There we go. And so this sometimes, if we're getting things in terms of capacitor and resistors, then that I is going to be replaced by a dq dt when you're going through and setting things up. So if you had a circuit where you have the E and then just this and this, so you have an LR circuit, then the total voltage, which is going to be forced by the forcing function E, is then going to be L di dt plus Ri. So this is going to be a second order differential equation. This is involving just a function of time. This is involving time, and that's the value I. So this is going to be a first order linear differential equation with constant coefficients. And then you can also have something with the RC circuits. I think there are homework problems I have people look at that were each of them. And then falling bodies. You've got acceleration is the derivative of velocity versus time. And then, of course, velocity is the derivative of position as a function of time. So acceleration is the second derivative of velocity with respect to time. But typically what we end up having is Newton's law is that the force is equal to mass times acceleration. And it's also, if there's only one force acting on it, it would be mass times gravity. So what you'd end up having is the equation dv dt, replacing the A, would end up being just, because it's acting downwards, it's negative, it would be just minus g. So you have a differential equation that's equal to a constant. With one of the homework problems that I asked people to go and look at with WebAssign is looking at the falling bodies problem number 17 in that section. And it reads as follows: determine a differential equation for the velocity of a falling body that has wind resistance and where the air resistance is proportional to the square of the instantaneous velocity. So resistance is then going to be subtracting off the resistance due to the force. So that's going to be mass times, that's going to be the force due to the resistance. So we're going to have that MA is going to be equal to minus mg plus, and then they said a force proportional to the square of the velocity. Proportional to means a constant times the square of the velocity would become v squared. So now if I were to get the A in terms of v's, we have a first order differential equation. We have m dv dt is equal to minus mg plus kv squared. And if they want dv dt by itself, then I would divide everything by m. And so I get minus g plus k over m v squared. Okay? So there are lots of real-world applications out there that differential equations are can go and used to be modeled. So from population growth to exponential decay, Newton's law of cooling, mixture problems, falling body problems, and there's several other examples throughout the textbook. Okay.